on three logical connectives. Actually, one of them is not even really a connective. The main focus is going to be on conjunctions and disjunctions. Right, so that would be ands and ors. We'll also throw in a few knots in there, so the opposite, complementary events. We will touch on implications, at least in the early going, it's not going to be very prevalent, but as we move forward, it becomes more and more, right? So the disjunction, the and statement, only true if both parts of the sentence are true, right? The or is true if either part of the sentence is true, and if then we'll get to in a little bit, all right? But I wanted to expose you to the Venn diagrams related to these. They're pretty easy to do. You'll want to use colored pencils when the time comes. I mean, you could get away with just using a pencil right now with just like cross hatching and stuff, but down the line you're going to want to have colored pencils. I have a ton here, so when I give you the assignment, I'll make those available to you. All right. But when we talk about A with the upside down U, that's the intersection between two sets. All right. So we're keeping it very basic at this point. We're just working with two sets at a time. All right. I'll challenge you with more complicated cases down the line, but not in the early going, obviously. All right. So the intersection is exactly what it sounds like. It's really where they come into contact with one another. You look at the intersection between two roads. That's when those two roads have parts that are in common. Intersection of two lines, that's the point in common. All right. Intersection between two sets, that's the area that's in common. And we learned in the last unit that area and probability could be kind of interchangeable depending on the circumstances. All right. So when I'm looking for the intersection of A and B, let's say I call this one A and this one B. What I would be doing is taking all of A, all of B, and see where the double shading exists. All right. So that little wedge in the middle, that's going to be your A intersect B. This little piece right here. All right. In a logical sense, we would use an upside down V, but when we get into sets, we use U's instead. All right. So it's kind of weird because it's really the same concept, but in different branches of math and even computer science, they use different symbols. So it's just the nature of things. All right. So when we talk about A union B, all right, so the union of two sets, what we're really talking about is combining them into one larger set. I mean, it says it right there. The typical example that I use is the concept of marriage. When you marry two ideas together, that could mean one thing, but I'm actually talking about matrimony, like two people getting married. One person has $10,000 in the bank account, the other person has $5,000 in the bank account. When you unite the two sets, now they have a total of $15,000. They're split among the two bank accounts, but it's still a combined set. Unless there's prenuptial agreements involved and stuff. You get into the law and all that. It gets overly complicated. I'm taking it back to like a third grader's understanding of marriage, right? Just keeping it simple. Two people, and they get rings and stuff, and then they go on their merry way. Right? So, but just to be a little realistic about it, there is sometimes when we unite two sets, I'll just do it over here. There is sometimes, I have auto shading on, let me just get rid of that. You have one person with their money in the account, let's say, again, $10,000. And then another person who's got their money in the account, I'll just leave the shading. And that other person's finances could get absorbed by the first person's finances. All right. So that would be the instance. So this is another case of a union. Where one set dominates another set. I'll figure out the shading later on. But once it's basically the instance where one person has $10,000, another person has $5,000. They get together, create one bank account where all the money goes, and it's in the name of person number one. All right. So that would be another instance of a union. But in this case, where we assume that there is just some overlap, what we would do is we would take person A, all their earthly belongings, person B, all their earthly belongings, and the union would be any part of the Venn diagram that's shaded. All right. So the first one is just the overlap. The second one would be any part that's shaded. Hated, shaded. All right. As cool as this looks, I gotta get rid of it. Delete. All right. Yeah, so not just the overlap, all of it. So really, I'd be looking at one final set that's everything that's covered with some shading. All right. Whereas in the first case, it's anything from one set that overlaps with anything from the other set. All right. So that other example of a union, we would be talking about everything that's in this circle. The typical example I use, and we'll get to the actual pure probability in probably like a week, maybe a few days. But if you roll a die, right, six-sided number cube, labeled from 1 to 6, and somebody asks you, what's the probability of getting an even number and or a 2, an even number or a 2? If you count all the even numbers, you're also counting the 2. So you would have accounted for the second set just by stating the first set. All right, so that's kind of a more practical example of this second union diagram here. All right, whereas if you roll a die and a simple case of rolling a die, and you're looking for a number that is prime or odd, right? You'd have some overlap, but you wouldn't. No, actually, that's pretty much the same example. One's covered by the other because all the primes would cover the even. So I'll think of a better example down the line, but basically there's something in common. It's just a question of whether everything's in common or only a little bit. All right. The complement of A is probably the easiest one. All right. So that little tilde means not. All right. So not A. So if I'm calling this set A, I haven't identified any other set. That other circle could be B, it could be C, it could be Omaha. It really doesn't matter. If I say not A, I'm saying everything except for set A. All right. We're only working with 2 sets at a time, at least in the early going, but there could be 100 different sets. All right. So if I say, in this class, for example, let's define A as a person who's wearing a white shirt or sweater or sweatshirt. All right. Only because I see 2 of you. So it kind of works out. So A would be you 2. Not A would be everyone else. All right. And we could define everybody else as one set of everybody else, or we could define it as each person being their own set. All right. In which case it'd have 3, 4, 5, 6, 7, 8. 8 different sets that meet the requirement of not being A. All right. So in terms of the shading, I wouldn't just shade outside of A and inside of this part here. I'd shade outside of A in total. So let me just. So all of this. Oh, I need this too. Yeah. Well, I like highlighters for this. Colored pencils are good. And like I said, when we do an assignment on this, I'll make those available to you. But highlighters really do the job nicer. Doesn't look much different on paper if you use a highlighter than what I did here. All right, so that would be the set of not A. All right, that whole box represents all possible outcomes that could exist for the experiment. All right, so in this scenario that I made up, it would be any color shirt that anybody could be wearing at any time. All right, so it allows for every other possibility, not wearing a white shirt or a white sweatshirt. All right, and if I define A as a white sweatshirt, then a white T-shirt wouldn't satisfy that. So that would be in the set of not white sweatshirts. You know, it depends on how you define things, right? Because what we're working towards, among other things, is being able to categorize as, well, I'll call it the haves and the have-nots. It's really the idea that you could have 100 different outcomes, but you could organize it so that it's into two groups: the stuff that you want and the stuff that you don't want. All right. So, you know, like you think about all the different types of weather that you could have, but I could simplify it down to it's either raining or it's not. All right. So keep it simple that way. It makes the probability easier to work with. You focus on, it's kind of like a controlled experiment. You focus on the thing that you want to test, and everything else is not that and needs to be accounted for. Right, but then you get problems like this, and I'll just do one of them so that you get some time to go back to studying. But if I want to take, for example, A and unite it with not B, sometimes it could be a little tricky. Some people could do it very quickly and easily without drawing like side sketches, but I like to do side sketches. So what I'll do is I'll just draw a box. I should just turn the shading off. I hardly ever need it. Oh wait, where's the shading option? Fill color, that's the one I want. All right. Like in the rare circumstances where I actually want it, it doesn't make it worth it to have it on all the time. Although it does look cool. It's just not ideal. All right, so copy this. Paste it here. All right, so this is, call it like an emergency situation. So like if I can avoid doing what I'm about to show you, I will, just because it is kind of tedious. But if I can't avoid it, because I can't figure out what the commonality is within a set, whether it's an overlap or an absorption kind of situation, you know, then I tend to want to draw it out. All right, so what we're doing here is we're looking at sets A and B. Do it a couple times. This first piece, I just want set A. Or I'm sorry, the first graph, I just want set A. So I just highlight set A. We get a nice blue here. All right, and then I want set not B. All right, so everything except for B. All right. So I have my set A, my set not B. What I would be looking for is not, because this is a union, I'm not looking for overlap. I'm looking for, when I combine these two diagrams, any part of it that has any kind of shading whatsoever. All right, so when I put this on top of this one, I look for any shading that might exist. All right, so really, it's only that like crescent moon part of B that's not shaded. So everything else would be part of the actual set. All right, so I'm able to determine what parts of the diagram are relevant by merging them together. right? So again, it's two separate things. Put it together, and just take note of any part that is shaded. Right, I'm going to leave them separate though. So everything except for that crescent moon there. Now you could shade it any way you want. I mean, if you want to use the like cross hatching technique, that's fine. You know, old school. Or get a nice highlighter going. I don't think the yellow and blue I chose would make this shade of green, but we know that yellow and blue do make green. Some kind of green. And so this would be my solution. All right. So anything out of whatever set you're dealing with that isn't just B alone. Right? So if I'm going back to the dice, if I say, you know, like I come up with an example that has some overlap, like the, you know, odds and prime numbers. Right? So if I say odds are the set of A and prime numbers is the set of B, then I'd be looking for anything that would just be not a prime number. So just be a composite number, right? Only. Can't be anything else out of the possible categories.
So if it were like the A and like the upside down U and then like the not B, would it be whatever's like double shaded?
Exactamundo. Yeah, so that would be, that's not my lasso. Double shaded would be that little crescent moon in A. And that would be it. And so that would be your answer for the next one, because it's the same. That's essentially that question. So, well, I don't need this anymore. But that would be just this little crescent moon. I'll go green. Oh, actually, no, it'd still be yellow. In A. All right. So at this point, I'll leave it up to you. If you want to continue working on this, you could try numbers 3 and 4, or you could go back to studying for the free response for tomorrow. All right. So we're looking at not A union B, right? The union is another way of saying or. So you'll see down under the definition for the next set of problems that I go back and forth between the logic connectives and the set notation, right? But when I'm looking for A union B, forget about the not for a second. I'm looking for any part of the graph when I merge the two, well, I shouldn't say graph, diagrams together, any part that's shaded, right? So what I like to do, I mentioned this last time. Oh, man. I thought I copy pasted it. Let me just do this real quick.
You can do it.
Okay, get rid of the shading. Actually, let me just turn the shading off temporarily. All right. Because I don't have the marker on.
Wait, do we just do everything that's outside of the circles?
Yeah, basically. All right. Just going to copy this so I have it locked up. All right, so if we're just focusing on A union B, we know that that's any part that would be in this, because this is one of the more basic.
Wait, do you have to fill that in?
Do you have to fill it in?
You don't have to fill it in where it says you have to.
Basically, the only thing I really need is the final answer.
Yeah, what you're trying to shade in. Yeah, what it says for you to shade in.
Yeah, exactly. All right, so this is A union B. If you recognize this, in theory, this is going on in your head. You're not actually drawing it out. But once you recognize that this is what A union B looks like, not that is ultimately what we're trying to generate. All right, so That would be everything outside of the two circles. So this isn't one where you'd have to merge two diagrams. I mean, I guess you could if you wanted to do set A in one diagram, then set B in another, and then overlap them.
No, that's too much.
Yeah, it's too much, and we already did it. So there's really no value in doing that. But for the next one, not A and not B, okay, that might be a little tougher to visualize. So what I'll do, I'll just kind of do it up over here, is I'm going to diagram out what not A looks like. All right, so not A would be everything outside of the A circle.
But there is no. Oh.
Not B would be everything outside of the B circle.
Yeah. So would it be everything?
We will see.
Oh wait. So.
Okay, so that's my not B. So if I merge my two diagrams, this is an intersection that I'm looking for. Okay, so the intersection would be anywhere where there's overlap. Right. So what we end up with here is something that's exactly the same as what we had previously. Right, it's the same diagram. I'm just gonna put this down here for later. All right. So what that gives us is an equivalence relation. All right. Not A union B is equal by definition to not A intersection not B. I forgot the not.
Can you just distribute the
That's exactly what's happening. You're distributing the negative, but it also impacts the connector. Right? Kind of like if you were to multiply an inequality by -1, you know, like you negate every term, but then you also flip the direction of the sign. It's the same idea here.
so union is inverse intercept?
Yeah, inversely related, exactly. All right, but it also means we could go the other way. So not A intersect B would be equal by definition to not A union not B. All right. So we're looking at two rules that we could rely on. Depending on the nature of the problem, it might be simpler to do, you know, if you're dealing with a probability question, it might be simpler to do it one way as opposed to the other. These rules are actually, they have a name. They're called De Morgan's laws. All right. And they're pretty useful. Now, we're going to get into conditionals in probability, and conditionals, I would say, are what make probability difficult. Right? If you're dealing with just ands and ors, conjunctions and disjunctions, it's actually pretty straightforward. It's when you have a conditional if leading to a conclusion, that's when things get a little dicier. All right, so there is a little typo here. I forgot to put the not in front of this one. All right, but this is the same as saying not P union Q not P intersect not Q. All right, so this notation here is the same as this stuff. All right, the benefit of knowing this is called the implication identity. Right, we could also call it law of implication. So we can convert from an if-then to an or an and. All right. So A implies B would be equal by definition to not A or B. Right? Well, I'll use the union symbol, or B. All right. So when you're trying to figure out what the Venn diagram would be related to an implication, we can take it and make it into a disjunction, and everything just kind of cleans itself up. I lost my blank diagram here, so let me grab another one. All right, so we need not A or B. So let me just get rid of the highlight here. All right, so not A would be everything outside of the A circle, which I guess I could have just copied over from before.
Not A or B.
B would be everything inside of the B circle. So if we merge the two together, all right, so we merge them together, anything that has any kind of shading. I'm sorry.
No, I just had 2 hours of sleep. It's not.
Is it a union or is it a dollar symbol?
This one should be a union. Yeah. So anything that has any shading whatsoever would be part of our solution. Right? So I can now create my graph. Basically, I'm going to shade anything that doesn't involve that little crescent moon part of A. Yeah, you should have seen it before. Venn diagrams isn't really anything unique to statistics, but really any conversation involving probability should really start with Venn diagrams. Right, so I know I can say right now my son in 7th grade is doing Venn diagrams. Not at this very moment, but like in the curriculum, the 7th grade curriculum. So there's a lot of repetition. Like pretty much everything we do starts with something that you've seen before, and then we branch off of that, as you remember from Unit 1. So the next one is really the same thing. Let me just put this aside. I have not A implies B. All right. And when I say implies, really what we're saying is that we have some kind of condition that's being met and a conclusion that'll come from that condition being met. All right. So in the first one, I could say if I get an A in the class, then I am a good student. All right. So I could that could be the real life scenario associated with A implies B. So if I get an A in a class, then I'm a good student, would mean the exact same thing as I did not get an A or I'm a good student. Right? It takes a little thinking to realize that they're actually equivalent to one another, those statements, right? Because there's often an implied if. So I call it playing the what if game. So you have not A or B. So I am not a good student. I did not get an A or I'm a good student. So I would think, all right, well, if it's true that I did not get an A, the alternative to that would be that I'm a good student. Right? If you're thinking of or in the traditional sense as it's a choice, I did not get an A or I'm a good student. All right. So if I didn't get the A, that might be the thing that's true. In which case, it doesn't matter if I got or if I'm a good student or not, because it would be overall a true sentence. But if I go the other way and say, you know what, it's not true that I did not get an A, law of double negation. So basically, I got an A, right? Or I'm a good student. Well, in the mathematical sense, or is something that could allow for multiple outcomes. If you think about like when you solve the quadratic and you said x is equal to 2 or x is equal to 3, you wouldn't say x is equal to 2 and x is equal to 3. I mean, maybe you did. Maybe you didn't even lose credit for it. If you were one of my students, you definitely did. You know that. Yeah, because you can't have a number that's 2 and 3 at the same time. All right. So when you say I have two solutions, either of them will satisfy the equation. You're saying x is equal to this value, or x could be equal to that value. All right. And there are certain circumstances where you could have multiple sets that overlap. That's what we're talking about here. Not in the case of the quadratic example I gave. But if I were to say that you have two solutions, x is equal to 2, and the other solution would be x is an even number. Now I'm looking at it as, okay, there's overlap, right? So one set accounts for all the even numbers. The other set is just a number 2. But since 2 is an even number, it wouldn't be a unique solution. Like one solution would absorb the other, right? So we have absorption laws and things like that that cover that, right? But this example here, number 6, is really just taking the rule that we came up with, right? Or saw written down right here, and just following that model. So if P implies Q is the same as, logically, not P union Q, and I'm telling you that P is equal to not A, so I'm going to replace the P with a not A, just the P, and I'm telling you that Q is equal to B, so I would replace the Q with a B, then I would get not A, so A, union B. All right, so the union of A and B, which I happen to already have from before,
Would it be A union? Yeah.
so A union B,
Because it's the because if it's not A, then it's
not that, yeah. Not the
it's
not A.
Not A.
Exactly.
There we go.
Yeah. Double negations are the bane of anybody's existence when it comes to contracts.
This is not
When you
A.
have a situation like this, can you just like
Not-
look at it and
not-
see,
not A.
okay, we've already defined that that's equal to P,
Yeah, I mean,
Q,
so like,
so like we can just say that, okay.
Just,
Yeah.
yeah, just do a quick swap. Yeah, exactly.
but this is not